Hello everyone, welcome back, and in today's video we are going to be solving two AITS problems from mechanics. So we'll pick up the first problem. So first we'll pick up this particular problem over here. Okay, so in this question we have been given two identical balls whose mass is m and they're connected to each other with the help of an inextensible massless string whose length is L. The whole arrangement is placed on a horizontal frictionless table with the string just slack. Now the ball B is given a sudden horizontal velocity v0 as shown in the figure. Just after the string becomes taut, we have to comment on the tension and the acceleration. Okay, so give this problem a try, guys, and then check out the solution. Okay, so this is how the situation is looking like. Initially the tension on the string was 0, guys, so and then we give it a velocity of v0. So just dt seconds after, tension will start acting along the string, and let's call the impulse due to tension force that acts for a short duration as jt. So now if you observe the x direction, the net impulse on the system is going to be 0 as the tension is now an internal force, which directly implies that the momentum in the x direction is conserved. So the initial x direction momentum is mv0 cos 60. And just after collision, what will happen is they'll move with the same velocity. Let's call the velocity as v. Okay. And the vertical velocity is unchanged because there is no vertical impulses. So it is still going to remain v0 root 3 by 2. So now completing our x momentum expression. So now this is going to be 2mv, and from here we get v as v0 by 4, and v0 itself was 1, so this is 1 by 4 meter per second. Okay guys, so now we have to determine the tension here. Now if we take block A as our frame of reference, then we have to reverse and add the velocity v, which means block B will only have a perpendicular component of velocity, tension force acting on the ball B. Now we have to be careful here because the ball A itself is an accelerated ball. So basically our frame of reference is non-inertial. That is basically the tension T acts on the ball A as well. So the acceleration of A is going to be T by M. So we have to add a minus MA component to our ball, and that would simply be T, right? So now we can write the force balance equation on the ball B. So that is going to be 2T. That is a force towards the center of the circle equals the mass times perpendicular velocity squared divided by the length L of the rope, which is 1 meter. And this, after solving, comes out to be 3 by 8 newtons. And 3 by 8 newtons corresponds to no particular option. Now we have to talk about the relative acceleration. Now let's just go back to ground frame. So let's forget about this. So the pseudo will be gone as well. So the acceleration of A is simply T by M, which is 3 by 8 meters per second square. And the acceleration of B is also 3 by 8 meters per second square, but in the opposite direction. So acceleration of B relative to A is going to be 3 by 8 plus 3 by 8, which is 3 by 4 meters per second square towards the left, and therefore D option is actually correct. So the answer to this problem is D. So now let's move on to the next problem. Okay guys, so this is a good problem to revise, how to write accelerations at different points in a rigid body. We have a hollow cylinder of a radius 4r, that is this big cylinder over here, that is performing fixed axis rotation with an angular velocity of omega naught. A solid cylinder of radius r is rolling without slipping with respect to the inner surface of the hollow cylinder. So this cylinder over here, it is rolling on the surface of this hollow cylinder. At the given instant, the line OC, okay, this line OC has an angular velocity of 2 omega naught as they have shown. The point A and B are the topmost and the bottommost point of the solid cylinder, and C is its center. We have to talk about these options. Okay guys, so it's given that the angular velocity of this line OC is actually 2 omega naught. So from this information we can directly find out the velocity of the center. It is going to be r omega naught. So and the distance of the center from the point O is 3r. So this is going to be 3r multiplied by 2 omega naught, which is 6 r omega naught. Now the big hollow cylinder is actually performing fixed axis rotation about the point O. So the point of contact on the hollow cylinder actually moves towards the left with a velocity of 4r omega naught. So as you can see, the omega has to be in the clockwise direction. So now we can basically equate the velocities at the point B. So the velocity at the point B, writing it with respect to a solid cylinder, it is going to be r omega minus 6r omega naught to the left, and this has to be equal to 4r omega naught to ensure no slipping. And from here we get omega equals 10 times of omega naught, which means option A is correct. Second question, they're asking the acceleration of point A. In order to do this problem, we'll actually take help of the point C. Now, with respect to point C, guys, so as there is no alpha, as the omegas are constant, right? So there is no component of acceleration in the horizontal direction. Okay, so if we look at the solid cylinder, it is rotating with an angular velocity of 10 omega naught, and it is translating towards the right with a velocity of 6 r omega naught, right? So now if I assume the center to be our hinge point, then it'll appear as if the body is performing pure rotation about the point C. So, and relative to center, you can easily write the acceleration of the point A. It is simply going to be omega square r towards the center. So that is 10 omega naught square times r. So the acceleration of the point A relative to the center is actually 100 omega naught square r in the downward direction. Okay, now we have to determine the acceleration of the center of mass. Now if you observe the point C, it is essentially performing circular motion about the center O of the hollow cylinder, and it is rotating with an angular velocity of 2 omega naught, and its circular radius is 3r. So the acceleration of the center of mass is going to be 2 omega naught square times 3r. So that is 4 3s are 12 omega naught square r in the upward direction. Now simply to get the acceleration of A, we have to vectorially add them. So it is going to be 88 omega naught square r in the downward direction. So option B is also correct. So now in the option D, they're asking us about the radius of curvature of point A. Okay guys, so if we have some random trajectory, something like this, and if we have a particle or block of mass m that has a velocity of v, and we know its normal acceleration at this particular point, then the radius of curvature of that particular point where the particle is situated right now is simply v square divided by the normal acceleration. Okay, so we are going to be using it right now. So again, the cylinder is rotating with 10 omega naught. Center is translating with a speed of 6 omega naught r. So the topmost point is going to be 6 omega naught r plus 10 omega naught r. So it will have a velocity of 16 omega naught r with respect to the ground frame. The acceleration we actually just determined, right? It was, and its acceleration is 88 omega naught square r, and it's normal only. So we can write the radius of curvature of point A as its speed squared divided by the normal acceleration. So this comes out to be 256 by 88. So that if you cancel out, it comes out to be 32 by 11 r. So even option D is correct. Now option C is actually pretty tricky, guys. So and the reason lies in the question itself. So they're asking the magnitude of acceleration of point B with respect to the contact surface of the hollow cylinder. So we have to bring the hollow cylinder into picture as well in this question. So let's just say this is our cylinder. It is rotating with 10 omega naught again. So now relative to the center, as I said earlier, it will have the point B, which is on the cylinder, will have an acceleration of 10 omega naught squared r, right, which is actually just 100 omega naught square. On the, I'm calling the material point on the solid cylinder as B, and let's say this is C. So acceleration of the point B relative to C is actually 100 omega naught square r in the upward direction. And the acceleration of C we earlier determined it was 12 omega naught square r in the upward direction. Now if the question was what was the acceleration of B in the ground frame, then you will simply add these two and you'll get the answer as 112 omega naught square r. But the thing is, the question was acceleration relative to the contact point. And let's call the contact point as just B dash. Now the contact point, guys, it is attached to our big cylinder. Let's call it B dash. And the cylinder itself is performing fixed axis rotation with an angular velocity of omega naught. So the acceleration of B dash, as B dash is performing a circle of radius 4r, it is going to be omega naught square times 4r in the upward direction. Okay, so what they essentially asked was the acceleration of the point B relative to B dash. This is going to be 108 omega naught square r in the upward direction. And therefore option C is actually wrong. Okay, so that was it for this problem, guys. If you have any doubts, you can comment down below. And do like, share, and subscribe if you enjoyed the video. And that's it. Thanks for watching.